Next, let's discuss excess air and combustion reactions. So in the previous example, we found that we needed 952 kilomoles per hour of dry air. That would mean that every molecule of oxygen got consumed and all of the molecules of fuel got consumed. But in order for that to happen, I would have to stir the stuff really well and wait a really long time for every single fuel molecule to find its oxygen molecule. So to increase the probability that all of the fuel molecules will come into contact with an oxygen molecule, I will supply excess air. I don't want to waste fuel because I spend money on that. So economically, that's a bad idea. Now, I'm going to be bringing in with my oxygen, I'll bring some carrier gas, which is nitrogen in this case. Sadly, it's going to absorb some of the heat of the combustion. If my goal is providing heat, which is what we usually use a fire for, then I'm going to need to come up with a way to balance how much heat is being provided and how much heat is being consumed by that extra air and that extra nitrogen. Also, we need extra oxygen so that CO2 rather than CO will be formed. So I'm going to need some extra oxygen. Now the analysis, it's a little premature to be able to talk about some of this, but we can borrow results from some other sources. So Engineering Toolbox has actually a nice little set of graphics on this. But here's basically what happens. If you have not enough air, you have too much fuel, or if you have more air, this is sort of forms a continuum of the ratio. This line right here is where you have exactly the stoichiometrically correct amount of fuel and air. So you are at that theoretical air stage. Now when you have more fuel than you have air, then at the end you would certainly have some fuel left. And the closer you get to being in perfect balance, you'll have less and less fuel remaining at the end of the reaction. However, it's not zero. There's always a little bit left. And so in order to get all of it to burn, I need to add air to my mixture of my combustion feed. I also carbon monoxide formation. Carbon monoxide formation is very high when I have excess fuel. It drops off as I have excess air and doesn't really become approximately zero until I reach a fairly high quantity of excess air. So these curves are showing what's in the product after combustion. I also, though, if I have excess air, I clearly am going to have some oxygen left afterwards, which somehow seems like a waste. But if you look at the efficiency, so how much heat is being provided by this, and again, this is something that we will be discussing how to compute the heat in a few more lessons, then the efficiency is going to increase as I add fuel or add air, but at some point, now that I'm just really spending a lot of time heating up that extra oxygen and nitrogen, and my efficiency will decline. So I really want to target where I have the maximum efficiency, which is going to provide usually a little bit of excess air. So if my goal is providing heat to, say, a boiler, then typical quantities of excess air would be, for natural gas, I only need a small amount, 5 to 10%. If I'm burning a fuel oil, 5 to 20%. The heavier it is, I'll need a heavier or a larger percentage of excess air. Coal requires a much larger excess air in order to burn completely, so it may be as much as 60%. But sometimes I do combustion not for the goal of creating heat. Sometimes I'm doing it simply as a way of, say, destroying hazardous material. That's what happens in the stack of a refinery, for instance. In that case, my goal is to have really clean air scrubbed as it leaves the plant and goes into the atmosphere. In that case, I do not want carbon monoxide. So I want to really make sure that I totally eliminate the carbon monoxide. I don't mind putting extra air back into the air. That's easy. That's a good thing. And so what I'm going to do is I'm going to really push it far this direction to guarantee complete combustion so that I'm not adding hazardous materials to the air. So I would go with 100% excess air, maybe even more, but 50 to 100% excess air in a stack environment is very, very common. Maybe I do more, but I'm not trying to provide heat, so I'm not worried about the efficiency of the combustion. I'm only worried about the formation of strange little things like carbon monoxide.